Good morning, everybody. Welcome to the first colloquium in this academic year, first colloquium of our faculty, which will always happen at exactly this time. There were discussions whether we should change the time and date. No, it will be as it was last year. 11, we start, 10:30, welcome for coffee. Normally in the hall, today exceptionally on the side. Our guest today is Dr. Grodner, Ernest Grodner from National Center for Nuclear Research, who is our fellow. He studied and made a PhD at this faculty at the Division of Nuclear Physics. Then he was a postdoc in Italy at INFN. And then he came back to us again, but after a while he changed to National Center for Nuclear Research, NCBJ, where he continues to do his research. Then something happened. Okay.
No.
There he made his habilitation thesis. Died. And starting from his PhD, actually, he was interested and pursued his interests on his research on nuclear chirality problems. Now he continues investigating collective phenomena in nuclei with different techniques. But also chirality, we shall hear about it. Chirality, the word comes from the Greek chair, hand, is such a feature of a phenomenon or theory or object which shows that the mirror image of an object or process is not the same as the process itself. And me personally, I have heard about chirality, of course, very often in the context of high-energy physics. It's a feature of high-energy theories, like my beloved quantum chromodynamics, of course, which is a chiral theory, but which is a chiral vector theory, but also has spontaneous chirality breaking as the origin of hadron masses. So for us it is very important. But also I have heard about chiralities in biology and chemistry. A lot actually in the chirality about chirality in biology. It seems it is connected to the structure of DNA in something which we expect is the origin of life. But I must say I heard very, very little about chirality in nuclear physics. So now we have this opportunity to hear it from the very best expert. I have to add that Dr. Grodner continues doing his research with the heavy ion laboratory here at the University of Warsaw, our neighbors, which presently celebrates its 30th anniversary. So symbolically, we have a lecture which will show us the achievements of this laboratory in that very interesting field. Okay, thank you, and Dr. Grodner, the floor is yours.
I would like to thank the organizers first for the opportunity to be here and to present our chirality study in atomic nuclei. And I'm also glad that I can meet the academic group with whom I have had the opportunity to work for several years in the past, mainly on theoretical subjects. Since we are experimentalists, we often needed decent theoretical support, and we have never been refused this support. So I'm doubly happy about my visit here today. As said, I'm not a theoretician, I'm an experimentalist, so I try to present a mechanism of nuclear chirality from an experimental's perspective, which I hope is not a very complicated one.
But would you also define what you mean by the nuclear chirality?
I will show. For the definition, please refer to two theorists. Yes.
I would like to know what we are talking about.
Yes, you will know.
I understand.
You will understand, I hope. So, let me start with some, okay, there are many mathematical definitions answering your question of chirality in different systems. But I would like to start with an intuitive way. How do we understand the word chirality in general? So in the most intuitive way, we understand it as the possibility of the system, of a thing or an object to exist in two somewhat equivalent forms. And I would like to start with a chirality example in everyday life, which is this citrus aroma molecule. And if you subscribe to Perfumer and Flavorist magazine, and I hope you do, then in 1993 you could learn that this molecule may exist in a right-handed and a left-handed form. And while the right-handed form smells like flowers or fresh fruits, the left-handed form has some unpleasant petrol-like, jet fuel-like smell. So it's better to know which handness should be used in, so to speak, everyday aromatic human affairs. In chemistry, like in other sciences, chirality relates to some static geometrical aspect of the system. Here we have another example. This is amino acid molecule that is also chiral. It has a left-handed and a right-handed form. And you see that the two forms differ purely by their geometry. So in this case, in order to map the left-handed system to the right-handed one, you need to use purely geometrical transformations, namely space inversion and pi rotation. Nuclear chirality is different. Here we have to deal with time reversal instead of space inversion. So the nuclear chirality is not a static phenomenon. There has to be some dynamics on which the time reversal may act. And this dynamics in a nucleus is provided by rotational motions present there. These motions are of both type, a single particle-like type, where a single nucleon has its orbital movement plus its spin, and also a collective type, where many nucleons rotate together. So actually, we need to have something like a mechanism inside, like a clock mechanism with rotating elements for the chirality to appear. And this picture shows actually the most simple mechanism required for the phenomenon of chirality to appear in a nucleus. This is an odd-odd isotope. It means that it is built of the odd number of protons and also the odd number of neutrons. And like people, nucleons like to pair up. So as many of alike nucleons as possible form pairs. These pairs in turn form a collective even nuclear core in this picture. This even core is shown as this oval shape here in a picture. This even core exhibits a collective type of rotation. So it has its own angular momentum vector shown here in a black color. As said, the nucleus is an odd one, so still there are two unlucky unpaired nucleons, one proton and one neutron. And each of those nucleons exhibits a single particle-like type of rotation. So a proton has its own angular momentum vector, here shown in a gray color, and a neutron, the unpaired neutron, also has its own angular momentum vector shown here in red. And it may happen that those three angular momentum vectors may form either a left-handed or a right-handed reference frame, provided that they span at least a three-dimensional space. So this is an ideal case where those three vectors are mutually perpendicular to each other, but they do not need to make this configuration. It is only needed that they span a three-dimensional space. So you can squeeze this geometry more and more, then gradually they will be less and less, let's say, chiral, until you squeeze it totally to one two-dimensional plane. Then there is no chirality. We call it planar configuration.
So that I understand correctly, this is your definition of the nuclear chirality.
The definition is purely mathematical, but this is a toy model to explain. What do we understand?
Yeah, but it violates time invariance.
No,
So moment.
no, it doesn't.
Then explain how
Give me a moment. I will reach this point. So, by acting of time reversal here, we reverse all those three angular momentum vectors to the opposite geometry. Then we transfer, we map the left-handed state to the right-handed one. So this, in combination with pi rotation, is the symmetry operator here. Okay, so as explained, the chirality may be defined in such a system for different geometries. They need at least to span a three-dimensional space, so we need to have a measure of handness. And the measure of handness of such a three vectors is just the mixed product of those three vectors. It is normalized, that doesn't matter. It's a mixed product. It's a standard definition of handness for a reference frame. So the handness value, when we take one convention, for example, the value of handness is negative for a left-handed configuration, is positive for the right-handed configuration, and is 0 when you squeeze those three vectors to one two-dimensional plane. This is important for the further discussion. Okay, so at the moment, I will answer your question, but at the moment, this is all the theory required to move on with the lecture. So now let me try to tell you how we experimenters, see the nuclear chirality phenomenon. So in an experiment, we need to produce a nucleus that is that exhibits a handness, at least for a while. So it means that it needs to have to be the right-handed or the left-handed in the left-handed configuration at least for some short time. This means that the nucleus needs to be trapped either in the left-handed state or right-handed state for a short time. And in turn, we need to have an energy minimum of the system, either for left-handed or for the right-handed configuration. And here we have a schematical picture of those two energy minima. So the nucleus may be trapped here or here. So we produce our nuclei here at the Heavy Ion laboratory in a fusion evaporation reaction. And our nuclei are excited, are very hot. And then they gradually lose their energies by emission of electromagnetic radiation, by emission of some particles. And then at some point, in order to lose even more energy, they need to select a handness by themselves. We call it spontaneously. And that's why it is often called a phenomenon of spontaneous symmetry breaking nuclear physics. Now I can answer your question, but you will give me 2 minutes more time. We are not, it is not a fundamental symmetry breaking. Hamiltonian is invariant with this pi rotation and time reversal. But the wave function may not be. This is what we call spontaneous symmetry breaking, not fundamental one. So it is not that general as other symmetry breaking phenomena. Simply speaking, this potential is symmetric. This is a Hamiltonian, right? When you reverse, you have the same, but the wave function not. So far, so good. But there is one major problem in experiment. And precisely because of this problem, nuclear chirality research took so long. And the problem is that we are unable to see this picture in an experiment. A gamma spectroscopy experiment is blind to handness. We are unable to see in which handness the nucleus actually may be. So the question then, then the question is, what the hell do we observe in an experiment?
In fact, if you would allow this state to live for quite some time, then you may look for the for exhibition of magnetic dipole moment.
I will talk about magnetic dipole moment a lot. You have no chance to look quickly in an experiment.
So this means that these states live for a very short time.
Yeah, that's right. And what do we see in an experiment? I will try to explain using an analogy. The analogy of the Schrödinger cat problem. And all of you perfectly know the gruesome story of this poor cat of Mr. Schrödinger. You know that there is a box. You know that there is a cat. Sometimes there are radiation sources. Sometimes there are two plates with a foot, one of which is poisoned. But always there is a guy here who puts all this together inside the box, seal it tightly, waits and observes. Okay, I suppose some of us are even too sensitive to listen to everyday's news on the radio, not to speak about this gruesome fate of this cat. So I will skip the details and go to the conclusions. And the conclusions are very well known to you. For a spectator, for an onlooker outside the box, the cat is neither, after some time, the cat is neither dead nor alive. So here we have a dead cat state, a live cat state. The cat may fall into those two minima, but we don't see it. We see the cat dead and alive at once. So we must deal with a state that is superimposed of those two possible configurations. And in nuclear chirality, we have the same story. In a laboratory, we observe states that are superimposed of both left-handed and right-handed configuration. There are, in this double potential well, there are two such lowest laying superimposed states. A symmetric one, which we call plus, and an antisymmetric one, which we call minus. This we are able to see in an experiment. Okay, those two states form an energy doublet. When you calculate the energy expectation value here with Hamiltonian, you utilize that the Hamiltonian commutes with the symmetry operator, the one with time reversal, and you have the result that those plus and minus states form an energy doublet around energy E0 with some energy splitting depending on some parameters mainly related to this energy barrier here in the middle. Simply speaking, The larger the energy barrier, the better the generation, the less the energy splitting. Okay. Now you may ask, do we expect to see only one such energy doublet in the level scheme of a nucleus? No. We expect to observe dozens of such doublets. Why? Because, as I said, there are rotational motions of nucleus, and these motions quantum mechanically exhibit themselves as presence of rotational bands, so sequences of rotational states. As I was a student here, I remember there was a perfect laboratory exercise where such rotational bands were observed in infrared spectrum of some rotating molecules. This was an exercise supervised by Professor Paweł Kowalczyk, if I remember well. So I will not explain why it is so. Please refer to this exercise if it still exists. But going to the conclusion, if we have a non-chiral nucleus, it also rotates and have a rotational band formed by those excited states, like this one.
I understand this energy difference for these two states is crucial, because if there is no energy difference, then
we don't see, yeah. Fortunately, there is no such a situation. The energy barrier is not so huge, and the splitting is non-zero still we can observe. But you're completely right. If the phenomenon would be ideal, then we couldn't see it in an experiment. So for a non-chiral nucleus, we have a rotational band. But for a chiral nucleus, this rotational band has to be built of those doublets. So dozens of...
This element of the doublet, do they have a different parity?
No,
I mean,
no,
they should.
no, it's not geometrical.
No, because they differ by the time reflection.
Tak.
Right? So element of if I have a state, a wave function, whatever, I perform a time reflection, the design should change for any of these states.
You have to do pi rotation together with time reversal. Time reversal alone is it's dangerous to discuss, right?
Because I want to say that also they have to differ because of CBT theorem. They have to differ by the parity these two states. Otherwise, you will violate it. So my question is.
No, it's not fundamental symmetry breaking. Hamiltonian.
No, I understand.
Yeah.
So my question is, if the elements of the doublet, do they have different properties under time invariance and parity invariance? Or they have exactly the same?
They have the same because they are superimposed of two handnesses.
So if they are superimposed, it is means that you have a different behavior under the time reflection.
No, in a laboratory, no. We can no.
What is the difference between these two states except for the mass?
And then you see, we have in an experiment, we see this. Always.
Again, I don't see your pointer. I mean, I don't see the.
Okay, this. We see this in an experiment.
No, you
Yeah.
observe the different doublet.
Yes, this form an energy doublet.
So my question is, all the quantum my question is if the quantum numbers of these two states are all the same.
No, there are special quantum numbers, which I will not talk about today because it's too much complicated. But this is not parity. There are other quantum numbers developed to describe the behavior of those states. I will not talk about this today.
You can distinguish between the
Yes, there is a quantum number called A. I don't know why, but they differ just by this A quantum number. And the definition is somewhat, to me, even somewhat complicated. So I will.
would expect that they should differ by the time reflection.
Those states
Yes.
don't. They don't. They don't. Time reflection does nothing to them. Maybe change phase of one of them, but nothing more. Okay, let's skip theoretical discussion because I'm not a theoretician. I'm trying to tell you how does it look like from an experiment point of view.
explain for experimentally. So what is plotted on the x-axis, on the quantum axis? So y
Yeah.
is the energy. What is the horizon?
The horizontal is, I forgot to tell that the horizontal is just the expectation value of this mixed vector product. So for the right-handed configuration, you have positive values here, and for left-handed configuration, negative values here. Okay.
It's just sum of difference between positive left-handed and right-handed. So both are together, but only the sign between them.
May I continue?
Colleagues, I suggest that longer discussion we postpone, because first, not everybody hears what is being said without the mic, and second, we lose
The time.
thread of logic. Abstain for the moment.
So we expect to see dozens of such plus and minus doublets, and we, as experimenters, plot it in a more easy to read form. We separate those doublets, and we expect to have two nearly degenerate rotational bands with spin and parity quantum numbers the same for corresponding levels. So let me go back in time around about a quarter of a century, go back in time to year 2000, around 2000. And this is the beginning of this nuclear chirality business. And at the beginning, the most experimental effort was devoted to search and identify such a two rotational bands, nearly degenerate, in some isotopes, to find it, to see if they are. And they were found in some, in few isotopes around mass 130. This is one of the first papers describing it. And at that time, I was accepted by Professor Krystyna Siwek-Wilczyńska to the nuclear physics division here in this faculty. And I joined a group of Professor Christian Droste. And I apologize, I don't have a photograph of Professor Christian Droste. I was looking for it last weekend on the web. And today, if something is not on the web, then it doesn't exist. So maybe it's occasion to make one photo with Professor Droste today. And we started thinking, what else can we add to this picture? I was confronted with this newly discovered phenomenon, and we started to think, what else can we do? So we took a look on this, and what do we see here, for example? We see those excited levels, but we do see also little arrows that are labeling an electromagnetic transitions between those levels. So we decided to focus on those electromagnetic transitions. And there was a fortunate event at that time. This was one of the very few, maybe too few events that I benefited from someone else's misfortune. And it was that Professor Brunon Sikora was forced to change his office, and most probably his new office was much smaller than the previous one, so it was impossible to keep all the books and documents. And Professor Sikora gave me this book. There is a signature here of Brunon. This is a book of Åge Bohr and Ben Mottels on a nuclear structure, an English version of it. I keep it today also. When I was at school, I had a Polish version of this book, and I knew perfectly that it's impossible to learn anything from it. You need to be a gamma spectroscopy expert even to read it, to try to read it. Despite that, I broke the ice, I could say, and took a look at initial chapters here, just to see how the English version is different from the Polish one. And immediately, something caught my attention. Almost at the initial pages, I found this commutation relation. We have here our symmetry operator, like here, but instead of Hamiltonian, we have an electromagnetic transition operator. So for Hamiltonian, this commutation relation leads to forming of energy doublets, and for some electromagnetic transitions, this commutation relation leads to doubling of transition probabilities. This means that the two rotational bands are expected to have similar electromagnetic behavior. And this is what we started measuring actually. So we were happy users of Warsaw cyclotron. We could organize experiments very quickly. And we got our first results around the year 2003. What do we have here? So we have the two rotational bands in our flagship case, cesium-128. And we measured the transition probabilities for some transitions in these bands. And here the levels are labeled by spin and parity. And here we have on the horizontal axis spin of the levels and the transition, electromagnetic transition probability here. Red points shows the transition probabilities in one of the rotational bands, so here. The black triangles show the transition probabilities here. You see, they match perfectly within the error bars. So we were very happy to confirm the expectations. The data analysis experiment was very simple, but the data analysis was very complicated and took half a year to get the remaining results. And this job was done with a great support of Julian Srebrny, who is well known here, and maybe less known Professor Alexander Pasternak from St. Petersburg. Finally, we got all the results also for the lower spin values. And it looks like this. And the problem was not that they stopped match. This was somehow expected. When the spin is, when there's less and less spin, the less dynamics is there to keep the chirality, I would say. So this was expected. But the problem really was that we observed the zigzag pattern here. So we have weak transition, strong transition, weak transition, strong transition, going down here in this rotational band. And this was not predicted at the time. No model predicted this behavior. So because it could be some error during the data analysis, we decided to repeat the data analysis. So half a year again. Same result. We changed parameters, everything, another half year, again the same result. And we tried the third time, another half year, so 1.5 years, finally, and the same result. What this picture does show? This picture shows that if you have best friends, you can't count on them if you are in a need. Why? Because our best friends in the nuclear chirality business in the United States, they were secretly working on theoretical descriptions of those bands. So they predicted, in theory, exactly what did we observe. Strong transition, weak transition, strong, weak. Here you have this new quantum number. So please refer to this paper if you would like to know more. I'm not a theoretician. I would like to skip it.
Since these two states have different behavior under time reflection, by definition, by your construction. No.
Let's continue. Okay. So we lost 1.5 years, but finally when we stumbled upon this paper, they didn't tell us. Then we knew we have already an experimental confirmation of it. So we published our first letter paper in the year 2006, although the results were much earlier. So as happy users of heavy ion laboratory, we organized another experiment immediately. Why? Because here we confirmed only a part of those selection rules predicted in the theoretical paper. And then we tried to see a complete set of those selection rules, and we measured cesium-126, where we see the zigzag pattern. I don't see the pointer now. When we see the zigzag pattern very clearly, and we confirmed the entire set of those predicted selection rules. And this time we published a letter in physics letters B. Why? Because the Higgs mechanism was published I think that year also, or close, in this magazine. So this shows that are different signatures of nuclear chirality that we expect in an experiment. Some existence of energy doublets, electromagnetic behavior of those bands that is similar, those selection rules, and there are much more. And this, to me, got very complicated. I don't see a direct relation between those pictures and this simple 3 angular momentum vector picture. So I asked myself a question, do we have something simpler? Why don't we measure just this geometry here and say if they are spanning 3-dimensional space or not? So I tried to answer this question, and now it is a clue for experimenters on nuclear chirality. I will return to the Schrödinger cat again. So when the cat is alive, when you put it in the box, it gets very excited animal, and then it supposedly got quiet and take one of the 2 configurations possible, right? This is this time on the axis is a cat's health parameter. So when you measure the cat's health parameter, the expectation value of it, you must deal with a superimposed state also. And you have negative, positive values. They cancel out. You will get 0 as an expectation values. 0 means that the cat is neither dead nor alive. I call it a hibernated cat. But what happens when someone put an already hibernated cat inside the box and seal it and waits? The cat cannot die, cannot break the symmetry, cannot wake up. It stays in one minimum in the middle. And that's all. His wave function is 1 minimum. When you measure the cat's health, this will give you again 0 value. So you have a hibernated cat as expectation value as a result of the experiment. So the experiment could not distinguish whether we have a symmetry breaking situation or not symmetry breaking situation. And the same was with nuclear chirality. When we try to measure handness, so here is this expectation value of this mixed vector product, this has given you 0 value in this case. And also for a non-chiral nucleus, this was giving you 0 value again. So the opinion was for several years that because of this, we are not able to measure the configuration of those 3 vectors in experiment. But I asked myself a question, but really, is it that, right? Why it is so? And the answer is very simple, because handness is negative here and positive here. And those values cancel out when you measure the expectation value. But do we need to measure handness? Maybe it's better to measure a volume spanned by those 3 vectors, right? Volume is positive here and positive here. And when you squeeze the geometry to 2-dimensional space in the middle, you will have a 0. So this is measurable. This will not cancel out.
Could you explain what the volume is?
I will. So this was easy idea, but yeah, the point was that we needed to find an experimental observable like this volume that is easy to measure also. And it turned out that this value is the dipole magnetic moment, what you was expecting at the beginning. Today, if you have some new idea, you look into internet, try to Google out if someone else did it previously. At that time, it was year 2008. I needed to go to a library in Chorza, Faculty of Physics in Chorza, and read textbooks. And to my surprise, in textbooks, the magnetic moment was not discussed for such a 3-vector systems, only for 2. So I needed to generalize the models to a 3 angular momentum vectors systems. And it was not difficult. I needed only a piece of paper, a pencil, and one afternoon. And the last component was the most hard to get because I was already married at that time. But anyway, I generalized that, and I ended up with such a formula here that is sensitive to mutual orientation of those three vectors. We have scalar products here. So this is like this volume, because not exactly the volume, because if the vectors are mutually perpendicular to each other, this gets 0 value. So for ideally left-handed, it has 0, and for ideally right-handed, we have also 0 value. But when you squeeze them to one planar configuration, this value becomes a non-zero. Very little, but it is. And this was the idea of the experiment. At that time, I was as a postdoc in Italy, so I submitted an experiment proposal to the nearby laboratory in France, and it was immediately accepted, and we did measurements. We got results, first experimental results, in 2010. But we published the results in 2018. Why it took so long? Because again, we encountered something unexpected. This is example how it is surprising to work at the edge of science. What was unexpected? So let me return to this picture. We have cesium-128. Here, for those states labeled in a black color, we know from previous results that most probably it is a chiral nucleus. But this volume measurement, this magnetic moment measurement, we did it only for this lowest laying states because the most easy to do. And it turns out that it is not chiral. No doubt about this.
Not chiral means what?
One minimum, not two.
No, but I mean, if you measure the magnetic moment, if it's not chiral, means that it's 0?
One.
Magnetic moment?
No. We expected 0. No magnetic moment. This is only a component in the equation. The remaining component doesn't matter, it's constant. So this is only the component that is sensitive to mutual orientation. And this component would be 0 for a chiral configuration and non-zero for planar, right? And the result was not 0, but this one. So we had the information that here it is chiral for higher spins and not chiral for the lowest spins. And this was not possible to reproduce by any models then, any theoretical nuclear models, because when you play with the parameters, then you could generate the non-chiral state here, but this will not reproduce the higher levels and vice versa. So we needed to wait for the theory to develop the right nuclear model, and so we spent a few years waiting on this and discussing with our friends in China mainly, and finally the model appeared that described this all correctly and reproduces the experimental results. And we have published a large paper containing the theoretical as well as experimental discussion in the large physical review C paper. But I would like to focus also on the experiment itself now, because this was a world record in making the cheapest experiment I have ever seen. Moreover, this experiment used only, we didn't use any complicated setup like you expect in high energy physics. No, we just used 2 small detectors put just on table. We also use one electromagnet like from 19th century, like from Julius Verne books, I would say. And this was enough to do the experiment and get the results. And so now I would like to show you the experimental details a little bit with some animation. I don't know if it will go. Yeah, we bombarded a target material with some ions here. And you know, when you have a fusion evaporation reaction, so it's a completely inelastic scattering, then the resultant starts to rotate. And this rotation is the vector, angular vector of this rotation is perpendicular to the beam axis. So initially we had a spin alignment of the nuclei we produced, and we had therefore an anisotropy of gamma radiation shown here. Then we put all this together inside of a external magnetic field. And then it happens that the magnetic field causes a spin alignment precession. And this precession frequency is the same for all the vectors. It doesn't matter which direction it points. This is a lucky situation. So we have a precession of spin alignment, and therefore we also have a precession of gamma radiation anisotropy, like here. Yes, it radiates when you see on top. Then we have a maximum of gamma radiation in one detector and minimum in the other one, and so on. So all we needed to observe is a fluctuation or oscillations of this gamma intensity radiation from our excited states. And here are those oscillations seen from the experiment. And therefore, we were able to measure precisely the G factor, so the value of the magnetic moment per 1 unit of spin in this red excited state of this nucleus.
Gamma radiations from the beta decay associated with the beta decay. What is gamma radiations from?
It's from the electromagnetic transitions, not beta.
Because usually arithmetic transitions usually do not break the parity, so they should be not aligned with the speed. So if so my question.
When you have a will I get 10 minutes more today? When you have one state, let's say with I and plus parity, and the other state with I minus 1 and the same plus parity, then there is M1 transition possible, E2, M3, and E4. You know, that's, I would say, it is possible. Right? I don't understand the question correctly, but there are electromagnetic transitions between rotational bands. Yeah? Not all, but some types are. Some multipolarities are. So we observed these oscillations of intensity, and last year we published a review article on this called "The G Factor Measurement as an Ultimate Test for Nuclear Chirality." So we discovered some method. We proved, there was proof of concept of some method how to see this 3 vectors geometry. So now I would go to the third part of this lecture today. It is answering the question why it is an important thing. Because you may ask yourself a question, okay, what did he measure? Some specific nucleus, some one isotope, cesium-128, specific one. Why it is important at all, right? So indeed, we did measurement in an odd nucleus, which has some quadruple deformation of this even core. But our colleagues, our competing groups, measured in other nuclei, and they found the possibility to form a chiral configuration also in even nuclei. Then you have to deal not with 2 unpaired nucleons, but 4, 2 protons and 2 neutrons. This is neodymium-136. Also, they have, okay, we have chirality in odd nuclei, in even, why not in odd even? So they did measurements, and they found a nuclear chirality in these cases too. And then, then we deal with 3 unpaired nucleons, 1 neutron and 2 protons, this case, right? Okay, previous cases were showing chirality formed by unpaired protons and neutrons, but why not only protons, right? So this is a single odd nucleus where chirality is formed only of unpaired protons, right? It is possible also. But this, ladies and gentlemen, is not all. initially, chirality was predicted in a few isotopes in the mass region 130, but it extended very quickly. You see in this mass region, there are many nuclei suspected to be chiral, and the yellow color shows here newly added ones. So today, if you look at the isotopic chart, where each pixel is a single isotope with neutron numbers and some proton numbers, then there are more than 60 isotopes that have been identified as chiral in different mass regions, not only this initial one around mass 130, but also with around 80 nucleons or around 200 nucleons. And this is not all. When we take a look at the gamma at the excitation level scheme of, let's say, neodymium-136, then we see that there are some rotational bands I was trying to introduce previously. The black ones were previously observed, and making a new experiment, another bands have been observed, the colored one. And it turned out that those new bands are partners to those previously observed. So two of such bands form those chiral partner candidates. So all in all, this level scheme may be formed almost of chiral states. They dominate the level scheme. Not chiral ones are only those here. So this shows why this is important, but that's not all. As I said, nuclear chirality that I presented until now was for nuclei with quadruple deformation, right? So the deformation means that we have a reflection symmetry of the deformed shape. But recently, it has been predicted that the nuclear chirality may exist also for octuple deformation of the nucleus. And octuple deformation looks like an egg, more or less. And you see, when you do the space inversion of this egg, it is not invariant. So it has a geometrical aspect of chirality. And if you have the rotations also, then you have this dynamical aspect of chirality on top of this. So finally, in such an octuply deformed nuclei, you expect not 2, but 4 nearly degenerate rotational chiral bands. A set of 2 bands differs by the other set by parity this time. But this is because of octuple deformation. Okay. Last year, there was a conference celebrating 25 years of nuclear chirality study. And this is the conference poster. We were invited to give the opening lecture for this conference. And you can see the beautiful conference site and a view of this from the lecture hall. Oh, yeah, very nice. Why I'm showing this? I'm showing this to show that nuclear chirality is treated seriously abroad, more and more seriously, and more resources are spent to study nuclear chirality. That conference was summarized by one of the inventors of chirality, Professor Jimeng, with this slide showing the chronology of nuclear chirality study, with milestones mentioned here, and 2 of the milestones are done here in Warsaw. Cesium-128, those gamma selection rules, and here Cesium-128 again, this G factor measurement. So we are happy about this, that we are still in the business. Now let me tell a little bit about the future, and I'm going to finish the talk. The future is that we are focused on searching how the chirality emerges in the nucleus. What are the mechanisms leading to formation of chiral geometry in the nucleus? So I will go back to this picture. We know that here we have, for the high spin states, we have most probably a chiral configuration, so two minima possibility for the nucleus to be in two left-handed or right-handed configurations. But also, the G-factor measurement told us that at the bottom we have only one minimum, and no, nucleus has not chiral features, doesn't possess. So the question is, what is happening here for those states labeled in gray? And now we are trying to measure this. We are using a different technique this time. Shortly speaking, those states are very short-living, and we were measuring them by measuring Doppler shift of gamma radiation for the nuclei that stops in some material. And the stopping time was around 1 picosecond, and that's why this method was sensitive within 1 picosecond range. But if you have longer lifetimes, then you need to let those nuclei be in movement for longer. So we do, this is called the plunger experiment. The target is separated from the stopper. The molecule, the nuclei fly in a vacuum for longer time, and that's why we are able to measure longer lifetimes that are expected here. And this is here in this gray area. And this is the job of our PhD student, Adam Nałęciawski, who is today here. He already submitted some proposals that have been accepted. This is one of them. And we perform these measurements here in Warsaw in a heavy ion laboratory. Also, we are invited by Chinese Academy of Sciences to perform some experiments in China. This is mainly Lanzhou University, and they would like to invite us to use their infrastructure and some advanced, more advanced techniques that are not accessible here. And most probably we will do experiments there, a new type of experiments there also. So I tried to, okay, the results which I have presented are the outcome of a teamwork. So I tried to mention the key persons during the talk, but there is one person left whom I would like to express my great appreciation, and who is no longer among us, Professor Grzegorz Rochoziński. Professor Grzegorz was the person who taught us all the aspects of a collective states in not only nuclear physics. He had lectures of quantum many-body problems in fermion structures or in boson systems. So these collective features I learned from Grzegorz, and to my surprise, this knowledge got very practical. Not only recently, we encounter collective states in many systems in science, and maybe the recently known one, which is on top, are those artificial neural networks. John Hopfield and Jeffrey Hinton. Those networks, these are just collective states of what they call neurons. I would call it bits. And also, especially in Hopfield networks, you can find something that resembles the chirality phenomenon. Namely, if you teach a Hopfield network to recognize patterns on the pictures like a zero number, then the network will have its energy minimum here, and when you feed this with a disturbed pattern, it will go down and recognize it as zero. But the Hopfield networks also have some symmetries, and they will recognize zero, but inverted zero too as well. So when you put the random noise as an input, then it will go and fall down either here or here. So this is something resembling a chirality in artificial neural networks. So this shows that it was really important to know the collective states from Grzegorz. And commemorating Grzegorz Rochoziński, I would like to end this talk and invite you for a discussion.
Yes, I see you are trying to activate the mic. Okay.
Let me return to the question to your. Let me return to your question on this very simple experiment which you have performed. When we apply magnetic field and you spin process, and you observe variation of gamma radiation in the detector. Oscillations. This means that the gamma radiation is along the spin or goes along the spin. It's preferred along the spin, and this violates parity invariance.
No.
It is known that beta decay
No.
is no. It's certainly is easy to prove because spin doesn't change under inversion, and the direction of the photon changes. So any correlation violates the parity symmetry. It's simple mathematics.
No.
There has to be something behind it. Certainly, the expectation is the correlation between the photon momentum and the spin. If you observe, it is an indication of the parity violation. Proof. Period. You cannot doubt this.
Okay. This is a very well-known technique to measure the magnetic moment.
Yes, but
Since years. Since years. Why parity? Why do you need parity to this? I really don't get it.
Electromagnetic transition.
Yeah, it's an electromagnetic.
Yes, which doesn't violate the parity.
No, why? M1 transition connects plus and plus parity states. Why this violates?
You cannot have electric radiation aligned with the nuclear spin.
Really, I don't get why it is so. Really, as you tell, this is a technique used for several decades to measure the magnetic moments on nuclear states.
But you measure by observation of the beta decay.
No, gamma only, no beta. Beta isn't, for us it doesn't matter. Beta is not observed. There is no beta emission at all. It's only gamma, period. Only electromagnetic.
More questions?
Historically, chirality in chemistry was observed in such a way that there were some molecules which are parity non-invariant, but these partners are simply non-existent. Typically, it was later on found that they actually exist, but usually have very different properties. But this chirality is very dramatic phenomenon. And can you see a chance that, for example, we would find nuclei in ground state that are such a chiral?
Okay.
Because you observe this phenomenon as a very subtle effect.
Okay. There are nuclear models that can predict if the nucleus in some state is chiral or not, and there is always a play with parameters that you feed to this model. Sometimes you get this answer, and sometimes you get that answer. So it's not easy to tell if this would be in a ground state for a long time or something like this. The problem is that the energy barrier between those two minima states, the left-handed one and right-handed one, is not huge. It tunnels much quicker than the time needed to emit a gamma quantum. That's why we do not see a handness in an experiment, in gamma spectroscopy experiment. But maybe in future, who knows? Some much quicker methods could be used to see. Everything depends on what is able in an experiment, actually. And now, gamma spectroscopy is unable to do it.
More comments or questions, please? I don't see any. So thank you very much for
Thank you.
discussions are still welcome.